Thank you. Yeah, I will be presenting joint work with my colleagues Ashu Tewari and Niranjan Subramanya on this topic. So before I go into the details of production surveillance, let me a little bit about generally the challenges in this area. So with the unconventional assets that we are seeing today, we have a larger number of wells. So in a conventional asset, you might have several tens of wells at most. Now we are seeing hundreds to maybe even thousands of wells in one asset. So you can imagine that the surveillance task becomes correspondingly more challenging. Then there is a drive for cost reduction. As I'm sure most of you are aware, the oil prices have been reducing significantly in recent years. Then finally, this is more from the sensing perspective. It's challenging to get an accurate measurement of a multiphase flow. So a multiphase flow is a mixture of, for instance, oil and water and gas, and it's very challenging to come up with a good sensor to distinguish between these three phases. So you will see that coming back in my presentation as well. So in order to get an accurate surveillance, we need to combine data from several sources. We need to do sensor fusion. So what's the objective for surveillance, as I will define it here, is that we want to get, for each producing well, we want to get the production per phase. So I should say, one of the things you're also interested, of course, in is the overall aggregated production, let's say at the gate. But to do surveillance, we need to be more refined. We really need to know what's going on with each individual well in order to identify issues, maybe repairs that need to happen. So there we really need that detailed information. So let me take you through a typical measurement setup that we have. So on top here, you're seeing producing wells represented by the rod pumps here. So one of the things we can measure is the total liquid rate produced for each well. So this is a relatively low-cost measurement, but it also has a high uncertainty to it. It's not a very accurate measurement. So secondly, we can measure the water fraction of each individual well. But this is a very expensive measurement. It's actually typically a manual measurement. And so as you can imagine, we'll typically not have many of those. We only have very few of those measurements. So final measurement that we have available is a test separator measurement. There, a number of wells, say 2 to 8 wells, are combined. And then we measure the total oil and water rate for each phase by gravitational separation. However, these are very big devices, very expensive devices. So that's why we cannot do this for individual wells. That's why we have to, what we call, commingle them, mix them, and then do this measurement. So as you can see, again, none of these measurements by themselves will give us our objective, which is the production rate for each phase, for each well. So we really need to combine all these measurements. So how do we go about this? We've chosen to use probabilistic dynamic models to address this challenge. So why have we chosen to use this type of models? Well, first we use probabilistic method because it allows us to fuse data with different accuracies that we are seeing, and we can quantify the uncertainty. Now this may excite you as attendees of this conference, but if we talk to our operators, they are not yet very excited when we say this. So the way we explain it to them is like this. So the way they typically do it now is with a more black and white approach. So there are ways to validate if a measurement is good or bad. So what you're looking at here, and I will show several of this kind of plots, is the oil rate as a function of time. And then looking at these metrics, say if a sensor has clearly failed or not, you either accept the measurement and use it, or you reject it and just discard it. So what's bad about this approach, of course, is that you're really losing data that you still might be able to use. So when we instead use uncertainty, we can salvage a lot of the data. We can basically use almost all of the data. Some need to be totally rejected, but typically we can still use more data. So this will lead to more accurate results in the end. Secondly, we have the dynamic model part. So what does that do for us? So first of all, we can get more accurate rates by combining current data with historic data. So remember I said that we have this water fraction measurement, but we don't get a lot of them. So maybe when you got it today, you can say, okay, this is the current water fraction and we can use it more or less as is. But what do you do when it's a week old or a month old? So a dynamic model is a very structural way to use that historic data. So in the example here, there's one measurement where the instantaneous oil rate has a very high uncertainty. By using the known dynamics of the production decline, we can use that past data to reduce the uncertainty in this rate estimate. Finally, we can do a production prediction by using, if we have a dynamic model, we can propagate into the future and then run scenarios on different interventions that we can make in the field. So this is the motivation of why we use this type of model. So how did we implement it? And I will go into these in more detail. But on a high level, we use a state space model for the dynamics. We estimate the decline parameters using probabilistic programming, and the production rate using a hybrid method that I will describe later. So we made this split because doing everything combined in a probabilistic program would lead to too high computational load. Remember, we have these thousands of wells, so we cannot afford waiting for minutes to get an answer from a very big problem. So first let me introduce the model. So we have two flavors of state space models. One with two-dimensional states per phase per well, and one with one. So let's start with the more complex one, which we call subspace 2. So here there are two variables again per well. One reflects the exponential, oh, that's the wrong button, the exponential decline, which is called Z here. So again, if we look here at the production rate as a function of time, we have these parameters, initial rate, then there is a half-life decline time, you could say. So this describes the exponential decline. But in practice, the declines that we are seeing don't look this clean. So we have to allow for random variations on top of this very sharp decline. This will give us the flexibility to adapt to experimental data that we are seeing. So this is quantified by the magnitude of the standard deviation of this random component. So this brings us to the total rate x here. It's a log normal distribution because the rate has to be positive. And so by the way, because we have a constant standard deviation here and it's the log normal distribution, this translates to a standard deviation that's relative to the magnitude of the signal. So what's good about this, it's a realistic decline model, it's kind of generally accepted model, and because it's highly informative, we have a low variance. But it can also have a high bias if this model is violated. For example, if the pump fails, you might see a steep production decline, which is in contrast, it conflicts with the decline model. So then at that point you could get a high bias in your estimate. So this brings me to the second state space model, which only has one parameter per well. So it's just a Markov process with a parameter A. So by the way, also in the first model we could write it like this in a recursive fashion, of course, because it's an exponential decline. But here we directly write it using that formulation with the A parameter in here. And again, process noise. We made this process noise proportional to the actual value to make it look as similar as possible to the state space model 2. So I will now show that there's a great dependence on the parameter values on how this model will behave. If you use parameter A equals 1, we get the random walk behavior. And so this is a simple model, and it will have a low bias but a high variance because there's a very high uncertainty, so it's very flexible to adapt to a lot of data. But if we don't, in absence of a lot of data, it will yield very high uncertainties. Whereas if we use estimated parameter values that are lower than 1, we get a decline behavior that's much more similar to the subspace 2 model. And so this will deliver us, while maintaining the lower complexity, a better bias variance trade-off. Maybe I should explain why I'm saying it has lower complexity. This is just because we have a lower dimensionality. We have fewer parameters per well. So that's the motivation in part of this simple model. Okay, so then I'll talk about the parameter estimation, estimating these decline parameters. So there we use a probabilistic programming language called Stijn. Probably many of you are familiar with this. So I won't talk in too much detail about it. But the nice thing about it is that we can more or less directly translate the equations that I've shown into a program. As you can see here, you can pretty much recognize the equations that I've originally shown here in the program. I won't go into too much detail on the other parts, but we need to add priors that we obtain from our knowledge of the physics of this production process. And we have to have a measurement model. I didn't really speak too much about it because it's a relatively simple model. We assume that we have an unbiased estimate, for instance, of the liquid rate, and with some measurement noise on top of that. And so when we have this complete program, we can actually estimate the decline parameters using Stijn. But as said, this is relatively computationally expensive. If you would expand this to estimating all the individual rates, you would get a very high dimensional space and it would just take too long. It works, we have made it work, but to accelerate this greatly, we need to devise a separate method for production rate estimation, so given the decline parameters. So for this we use a mixture of Gaussians. And so the benefit of this approach is that we can, in many cases, analytically propagate the rate estimates over time. So we don't need to do sampling in many cases. And which are those conditions? Well, if we don't hit the rate constraint, remember being that the rates have to be positive, so we don't have negative rates. And we have to have linear measurements, which occurs in most of the time. So for example, the liquid rate is just the sum of the oil and water rate, so that's linear in the parameters. The only one that's not linear is this water fraction measurement. As the word says, it's a fraction, so this is a non-linear measurement. But we don't have too many of those. So in this situation, we can do very convenient, very low computational effort computation. Then there's a case where we will hit the rate constraints, so our posterior would expand below zero significantly. And at that point we have to resort to a sampling-based method, so we'll use importance sampling here, because we have a very good candidate distribution from which we can sample easily. And then we basically only have to perform the truncation at zero. Then secondly, we may have a nonlinear measurement, so this water fraction measurement. In this case we use again Stijn to do Monte Carlo based sampling, because here we do not expect that our prior distribution and posterior distribution are very similar, that we expect them to be very different. So that's why in this case we use Monte Carlo sampling for these situations. So this ends the part about how we use these models. Now I'm going to show what's the benefit that we can see. So I'm going to show simulation results here, because in those cases we know the actual rates, which is pretty hard to get to in the experimental situation. So let me first show you some example data. So we've done many repetitions of the same setup to get statistical significant, statistically accurate results. So again, we're looking at rate as a function of time, but now for three different methods. One is a deterministic method, as we call it, which doesn't take into account uncertainty. You can find the details about this method in the paper, but we use this as a reference method, as it could be used in the field today. Then secondly, we have the subspace 1 estimator that does rate estimation, but it uses fixed parameters. So that's already better than the deterministic estimator. By the way, the plots look a little bit different because this estimator now also reports an uncertainty, where the deterministic estimator just only gave a value. Then finally, we can use a model where we do parameter estimation. And this, as we will see in the final results as well, does better, still better. So these are the results, the absolute error between the predicted posterior mean of the rate and the actual rate that we know, again, because this is a simulation experiment, for three cases of increasing challenging situations, so more process noise and more measurement noise. And roughly how I can summarize these results is that compared to the reference method, the absolute error for the subspace 1 method is a factor of 2 lower. And then when we add the parameter estimation step, we get results that are a factor of 4 better compared to the reference method. So these are significant reductions in error, obviously. So to summarize, I've shown you how we can make this split between parameter estimation and rate estimation, and this will deliver us a method that doesn't have too high of a computational load, allowing us to use this in a field with thousands of wells and getting reasonably fast answers. I think the most important contribution of this work is not so much how we did the implementation, but I think the choice for using a probabilistic dynamic model is our real contribution to this area, because this wasn't done before, and we have brought that technology to this problem. Thank you.